Okay, let's look at some common sums. The first is this one here. You start at the index 1 and go up to k. So in fact, there are k terms altogether, and each one is 1. Also, actually, that's k times 1, which gives us k. Let's look at our next example. Sum of the integers from 1 up to k is denoted by this sum here. To show the technique of evaluating these sums, let me do 1 up to 7. All right, now, if we do this, then we can group these two, get 8. If we group the second with the second to last, we get 8. If we group the third with the third to last, we get 8. And then we have a 4 left over. Now, of course, we can add these terms in any order we want. So we actually have 8 plus 8 plus 8 plus 4. So it's actually equal to 8 times 3 halves, times 8 times 3.5, which is 8 times 7 halves. Now, where did this 8 come from? Well, 8 was the first plus the last. Where did this 7 halves come from? Well, that's half the number of total terms, right? We have 7 terms total. 7 halves is the half the number. All right, so 8 is the first term plus the last term, so that's going to give me 1 plus k, or k plus 1. 7 over 2 is k over 2. And we have our formula here. We've derived it. Now, you can use the same reasoning if you start the sum at a and go up to k. Think about how you do that here. First plus last, second plus second to last. Now, what are you getting when you take the first plus last? That's k plus a. So you're going to have a whole bunch of k plus a's. How many k plus a's will you have? Well, you'll have half the number of terms. What's the number of terms? Well, it's actually k minus a plus 1. You can work that out. For instance, if I had a equals 3, 4, 5, so this was a and this is k. If I take 5 minus 3, which is 2 plus 1, there are 3 total terms. And you can convince yourself with several examples that this is, in fact, the correct number of terms. So here's your general formula. Now here they ask you to find several other sums. Now you can get these sums by manipulating the formulas up here, or you can use the same method to derive the formula yourself. Now let's consider some infinite sums that you may have seen before. Here is the geometric series, and you have sum from I equals 0. Notice we're starting with 0, and we're going up to infinity, so we have 1/2 to the 0 plus 1/2 to the 1 plus 1/2 squared, and so on, which comes out to be this. And I'm sure you've seen this trick in high school. There's a way to sum this up to get this value. And I'm not going to do it. You can go look on the web or your high school text and find this out. But this is a geometric sum of geometric series. Now, in general, instead of using 1/2, I could use x, and the general formula is the sum of this infinite series is 1 over 1 minus x. Well, actually, I didn't notice. The proof is right down here. If you let s be the sum and take x times s, and then you subtract these two equations, all the terms over here cancel except 1. That should be a capital S. We get the total for the sum. We can use a similar method to prove this sum when you have a finite number of terms. And we've seen before, if you multiply by a constant, the constant can just be brought out of the sum. So notice there's an a here and an a here. That doesn't change anything. The geometric sum gives you this same denominator, 1 minus r, which compares to the 1 minus x up here. But if you have a finite sum, you have this 1 minus r to the n, also in the numerator. And you could actually prove this the same way you prove this one. Here are some other formulas from calculus. This is actually the Taylor series for e to the x. This is the Taylor series for sine of x. And we can write these using this summation notation. Notice that the exclamation point means factorial. If I have n factorial, that's equal to 1 times 2 times 3, all the way up to n. Multiply them together. Here are some series that have no sum. In other words, they go to infinity. The sum of fractions, integer fractions, 1 plus 1/2 plus 1/3, and so on. Or you can take a geometric series when the absolute value of x is bigger than or equal to 1. In this case, the terms all grow in size, and you get infinity here. All right.